So we are looking at page 14 in the notes, and we're going to look at energy transfers and how we describe them. So we know that energy cannot be created or destroyed. The total amount of energy before a change occurs is the exact same amount of energy that is present after the change occurs. But we now understand that energy can change its form, change from chemical to electrical to light. We also understand that energy can be transferred from one material to a different material. So we have two terms that we will look at quite a bit this year to describe the direction of energy transfer. So these energy transfers, they supply the direction. So we have these two terms, exothermic versus endothermic. So take a look. We have the term exothermic, and it starts with EX, like the word exit. So when you go through an exit, you are leaving that building. Well, what is exiting? We have this little partial word therm, which is another word for heat. So this is when heat is leaving a material. So the big thing is learning our point of view. Which material is our point of view? So the material that we are monitoring and most interested in, we refer to as the reactant. So the reactant, this is our point of view. So point of view. So our point of view, our material of interest, we call it the reactants. And so the heat leaves our reactants. So the definition says the reactants release heat. So it starts off in our reactants, it exits our reactants, and the heat doesn't disappear, but it goes into the surroundings. And the surroundings, this is every other material except our point of view. And so the reactants release heat into the surroundings in order to make the products, to go through that change. And as a result, the surroundings warm up. So here we go. Here is an example. So we have this beaker, okay, and this sample inside the beaker, this is our reactant. So that's our reactant. And our reactant is in the liquid phase. So I'm going to put liquid reactant. And this liquid reactant, it actually transfers or heat exits. So when enough heat exits our reactant, it no longer is in the liquid state, but enough heat has exited, and all of a sudden we look at our sample and we no longer see liquids, but we see chunks of solid like ice because enough heat has gone out. So the heat has gone out, left the sample. So we have a type of diagram to represent this type of transition, and they're known as potential energy diagrams. We will do more with these diagrams later on in the year, but they all look pretty much the same. So you have your XY axis, okay, and the x-axis, it represents the reaction in process. The y-axis is the potential energy. So we could just say that we start off at a value, down here at the origin, it's 0. And as you move away from the origin, the numbers get bigger. And of course, I can't write sideways, but these are measured in joules. So it's the amount of energy. What you will notice for a potential energy diagram, there are these two platforms. The platform, the closest that touches the y-axis, represents the reactants, what we start with, our point of interest. The platform more to the right represents the result of the change. So I'm going to write result of the change, what we're going to end up with in our container. What we see here is that there is a hill that connects our two platforms. And every time you leave the reactants platform, you always head up the hill. And then you reach the peak of the hill. So we're at the peak of the hill. And then once you reach the peak of the hill, to reach the product, the result of the change, what is produced, it's always a downward slide. So in this case, as we learn in chemistry, to go from the reactants to the peak of the hill, look at our numbers get bigger. So that must mean that we are going to take in or absorb energy. Then when we reach the peak of the hill and we go in the downward slide, now we're going from larger numbers and we're going down to lower numbers. So this must mean that energy is being given off or it's being released. Okay, so in this case, if you just compare the length of the uphill trail to the length of the downward side of the trail, going from the peak to the products, it's a much longer ride. So there's more heat released. So more heat is released. So we're going to write here. So in every exothermic process, more heat is released or given off. So when we get to the point where we write reactions, what we see is that to the left side, we put our reactants. And down the road, we'll put actual chemical names or chemical formulas. Arrow, the names or formulas of the products that will be produced, but now we have extra energy or heat. So on the product side, we will see more heat left the reactants than joined or entered the reactants. Okay, looking at the other side of the notes. Okay, so now we have the term endothermic. So it starts off with en, as in the word entrance. So when you go through an entrance, you are going in. Well, in endothermic, what is going in? When we take a look at this word, we see the little word therm in there, which we now know refers to heat. So in an endothermic process, heat goes into our reactant. And remember, reactant is our point of view, the material that we are tracking and interested in. So in order for heat to go into our reactants, the definition simply states that the reactant absorbs heat. Now remember, that heat doesn't just come out of nowhere. The reactants absorb or take heat from the surroundings in order to make the products. So as a result, the surroundings are giving away heat, so the surroundings will cool down. So once again, we've got a beaker here, and inside this beaker, that gray stuff, this is our reactant of interest, and it's in the liquid state. This time, heat from the surroundings is going into our sample. And when our sample absorbs enough heat, okay, we start to see a change that occurs. So I'm not the best artist here, but we start to see that our sample starts to boil and some of that liquid starts to escape as a gas. So we see a liquid changing to a gas because enough heat went into our liquid reactant. We have our potential energy diagram. And if you take a look, it looks pretty darn similar to the exothermic. So once again, on the y-axis, we have the potential energy, which is measured in joules. And when you leave the origin, so the origin, we can say the number of joules is 0 near the origin, and as you move up it, the number becomes greater for the scaling. We have our two platforms, just like in the other one. The platform closest to the y-axis is where we start, the reactants. What the heat energy is going into, and the platform farther to the right is the result of the change. So products are what are formed. So it's the result of the change. And like before, you can see that there's a hill that connects the two. And every time you leave the reactants platform, it's an uphill climb. So you're going from, if was more scaling, you would start at a lower number, and by the time you reach the peak of the hill, you're at a much higher number. And so when you go from a lower number to a higher number, you're gaining. So that would mean that heat is being absorbed to get the reactants energy up to a higher value. But once when it reaches that peak, then it's a downward slide from the peak to the products. And if you watch what happens to the numbers, you go from a higher number and you drop down to a lower number, which represents that heat is now leaving or being released. So we read these potential energy diagrams the same way. But in this case, we'll notice that the side of the hill that goes reactants to the peak is much longer than the opposite side peak down to the products. So what that indicates to us is, in this case, more heat is absorbed. And because more heat is absorbed than released, we would classify this overall as an endothermic process. So now take a look how we might show this in a reaction. So like before, we always start with reactants names or formulas, but these reactants don't have enough energy to make the products. So it's the reactants plus that heat energy. And when they have taken in enough heat energy, then they are able to form the products. So if it's an endothermic process and we see it written as a reaction, we always will see heat or energy shown on the same side as the reactants. Now here is sometimes the harder part that takes a little bit of work to wrap your mind around. Learning the definition, exothermic, endothermic, most students get that right away. Exothermic, heat exits, leaves the reactants. Endothermic, heat is absorbed or enters into the reactants. Usually get that pretty quick. How do you determine, looking at lab data, was the reaction exothermic or endothermic? So when we collect lab data, we actually monitor the temperature of the surroundings. So we monitor what happens to the surroundings. So our best examples of the surroundings is going to be the air. Does the air does the air seem to get warmer or cooler? Water. Many times we will have a reaction or a change occur in a container of water. What happens to the water's temperature? And then sometimes there's enough energy that's transferred that we can actually just feel the change of, like, the container that's holding the reaction. Like, we can feel the sides of the beaker or test tube. So I'm going to write beaker and put in parentheses the container. So this is kind of the big idea. So if the surroundings warm up, So you're watching the air temperature, and the air temperature before any change is 21 degrees Celsius. And then a reaction happens, and then you start to look at the thermometer that's just in the air near the container of the reaction, and the temperature starts to climb to 25, 27, so it's heading towards 30. That means that the surroundings are warming up. That means that the reactants released energy. So the reactants went through an exothermic process. So the opposite is also true if the surroundings cool down. So you have a container of water, you measure the temperature of the water's temperature is 20 degrees Celsius. You dump some sort of reactant into the water and stir it, and all of a sudden you start to notice that the temperature starts to drop below 20. It becomes 19, 18, 13, 10 degrees Celsius. So if that happens to the temperature of the water, then that means that the reactants absorbed and took heat away from the surroundings. So the reactants absorbed the energy. So I'm just going to say that the last part is where we need to do a little bit of practice to help us really master that idea.